Hi, pal. This is Tony Lockwood. I'm here at the CAASE conference. We're in Cleveland, Ohio, and this event is co-sponsored by Digital Engineering that I represent and the NAFINS organization, who should be representing you. Okay, I have a very special guest here with us. He's a lot smarter than I am, and so I'm going to let him do most of the talking. Would you please introduce yourself, tell us who you work for, your title, what your company is up to?
Yeah, thanks a lot for the invitation. My name is Karl-Michael Nigge. I'm working as head of product management for a company called Volume Graphics. Possibly not known so much in the simulation world yet, but that's why we're here actually. Mm-hmm. We're coming from the world of CT, the world of industrial computed tomography. I have noticed yesterday in my talk that quite a few people in the simulation world are already familiar with what CT is, so that's a very good trend to see. We're very happy about that. Mm-hmm. What we are making is software to analyze CT data, industrial CT data. We don't have anything to do with medical. We're just focusing on CT, mm-hmm. and I think it's fair to say that we were the pioneers of industrial CT software.
Well, I can tell you, I was walking around the show, and you have some stunning demonstrations on at your booth here, and these are available at your website, I presume.
In some form or the other, they are available on the website. Yeah.
Okay, we'll get that web address to everybody because you got to see this stuff in action. It's great. But go on now. Tell me. Let's put it this way. I'm an engineer. Okay, and the machine broke or something like that, and we're trying to figure out what happened to the metal. Is that what's going on here? Where do you fit into the flow of manufacturing and design and stuff like that?
Yep. Well, actually, industrial CT is used in basically all different phases of the life cycle of a product, mm-hmm. starting with the engineering and development, actually even starting one step before when it is about materials research and development, mm-hmm. then moving into component development, and then, of course, going into quality assurance while the production is running, and up to and including damage analysis for components which are in the field.
Right.
In terms of what you can do with industrial CT, there's basically three different areas. One is looking at the dimensions of components. Mm-hmm. A lot of quality assurance of industrial components is about measuring do the dimensions fit. Yeah. Because ultimately a component must fit to another one, so you have to measure.
Right, and it has to be.
That's
an airplane, you don't want it, and it kind of fits. Just
in any part, you don't. You really want it to fit.
Yeah.
I mean, depending on the type of component, of course, the established methods for metrology are tactile methods or optical scanners. Mm-hmm. But whenever you have a component with interior structures, which are hidden for the visible light, then you typically want to turn into computed tomography because you're using X-ray, you're generating a 3D representation. You could even say you're generating a digital twin of your object.
That's right.
And that can be used to measure dimensions, to do all the geometric dimensioning and tolerancing according to all the ISO norms. Mm-hmm. That's the one area. The other area, and that's the one that makes even more use of the capability of looking inside the component and looking inside the material, is doing all kinds of material analysis. Mm-hmm. So, for example, if you have a fiber compound material, you want to know about the fiber orientation, or you want to know about the fiber volume fraction that's inside your material. All of these things can be analyzed very precisely with our software. Mm-hmm. Or for example, if you have foam structures, like I'm first talking about intentional porosity, so to say, like metallic foams or ceramic foams, or more recently the lattice structures, which are very much in fashion in 3D printing. It's kind of a new type of material. You can analyze these types of materials as well. You can analyze the size of the porosity, the volume fraction of the porosity, and things like that.
Now, what sort of computing overhead are you best with? As I said, I saw some stunning graphics. Do you recommend just a really good workstation, high performance computing? all of the above work on?
Well, you don't need to have high performance computing to use computed tomography.
No. I mean your software, your analysis.
Well, it depends a little bit on what you're doing. The one step which is kind of computationally intensive in computed tomography is a reconstruction. So meaning the conversion of the projection images into the 3D volume representation. That's, let's say, some tough mathematics which is behind there.
Right.
And that also requires quite some computational power.
Right.
But you can do it on a workstation with good graphics performance. So it's nothing very special in terms of computation these days.
All right. No, it was funny.
And,
now, what are your clients, your customers, your users asking you for? Are they asking for more features, different forms of analysis, anything like that? Are they, what are they facing that they're turning to you? Help me with this. Is there any trends you're seeing there?
Yes, there's actually one trend which is linking what we're doing historically to the simulation world, and that's the trend of, let's say, getting more conclusions out of the data. One classical example is since many years CT has been used to look at porosity of cast components, for examples, or more recently of 3D printed components. Now the classical approach is, in some ways or the other, you come up with a porosity specification, and you can use that as a tolerancing criteria in our software, and then you say part is okay or not okay.
Right.
But what's even more interesting is to really understand, well, is the porosity that I see in my component, is it harmful or not? And that's something which it's a good topic for simulation. At the same time, it's a very tricky and difficult topic for simulation.
Right.
I would venture to say that there's among the, let's say, established simulation approaches, and here I'm talking about classical FEM simulation, it's quite difficult to tackle that problem at the component level. Maybe you can solve it at the level of small material probes, but really looking at a cast component with lots of porosity inside and figuring out, well, does this porosity make a difference in terms of the mechanical stability of the component? That's quite a difficult task, but actually we do have a very interesting solution for that. Because, and that's the third area that I was going to mention before that we are into, is actually simulation. May come as a surprise, and we're using a different approach to simulation. We're using, you as simulation experts, you know that it's the immersed boundary method, which is maybe more known from CFD rather than from mechanics simulation. So I'm not claiming we have invented that method, for sure not, but we have applied it to the problem of porosity simulation, or simulating the effects of porosity, and it comes with tremendous advantages for that problem, because the biggest challenge that you would have in a classical FEM simulation when trying to simulate a component with porosity would be the generation of the mesh. Either you make it too coarse, then you kind of don't really capture the pores. If you make it fine enough, the mesh gets so large that you run into computational problems. You're just at the end of your computational capacity. And the approach that we are following is working directly on the CT scans. You don't need to do any meshing at all. You just take the CT scan, then you do a porosity analysis, which is a standard functionality in our software, which is, by the way, not that computationally intensive either, even. And then, based on that porosity analysis, you use our simulation. All you need to do is tell our simulation, use that porosity pattern, and then you get the stress distribution in your component. And in that way, you can actually see whether the porosity makes a difference, because actually you can do the same simulation, of course, in an external software. That's what you normally do. You can also do the simulation on the CAD model within our software, just for comparison purposes, and then you can even calculate the stress difference that comes from the porosity in the part. And that's really what you want to know, whether your porosity makes a difference or not.
That is really cool.
We think so too. And
that is really cool. Folks, wow, Volume Graphics. Their website is volumegraphics.com, and you can write us at the DE editors if you missed that. This is cool stuff. Go to that website, see some of the stuff on there. That is really, really cool. Thank you so much for your time. Thanks, pal.